Hello everyone. In today's lecture, we are going to discuss about ARM programmer's model. So what is meant by a programmer's model? It refers to the abstraction of the ARM processor's internal architecture that is visible and relevant to a programmer. It includes how a process is being done. It includes the registers, the modes, and the memory organization that the programmer interacts to write programs in assembly language or under a high level language that operates at hardware level. This is the programmer's model of ARM Cortex-M0. ARM Cortex-M0 processor has two operation modes and two states. The two operation modes, the two states are thumb state and debug state. If you see here, you can see this is a state and this is a state. And two modes of operation is there. One is handler mode and another one is thread mode. Right? So this is a programmer's model. So when a program has been executed, which state will it be inactive, or which mode will it work on? So this is what this thing a programmer should know, right? And so programmer's model in ARM Cortex M0. When the processor is running a program, it is in the thumb state normally. So this is thumb state, this is debug state. If any debug activities occur, then it moves to the debug stage, and once at a completion, it returns back. So when it comes to the debug state, the processor starts executing the instruction, right? And when it is in normal thread mode executing, when a normal code is being executed, then this thread mode will be in operation. When if any request or interrupt comes inside, then the request is being given to the handler mode, and then executing exception handlers, which for which processor this could be, for which what are the resources available, all this will be checked, and then exception return. Again, after completion of this interrupt, it will return back or resume to back to its normal position. In this state, it can be either in the thread mode or the handler mode. The only difference is that thread mode can use a shadowed stack pointer. That is another one stack pointer which is similar to this stack pointer. That is shadowed stack pointer. The debug state is used for debugging operations only. Halting the process stops the instruction execution and enter debug state. This state allows the debugger to access or change the processor register values. The debug can access system memory locations in either the thumb state or the debug state. When the processor is powered up, it will be running in the thumb state and thread mode by default. So these are the registers, and already we have discussed about these registers. We have 15 registers. Out of these 15, R0 to R12 are general purpose registers. Then R13 is stack, R14 is link register, R15 is program counter. Then we have two stack pointer registers, and here few special function registers are there. If data from memory is to be processed, they have to be loaded from the memory to the register in the register bank, and then it will be processed inside the processor and then returned back to the memory if required. This process is known as load store architecture. The Cortex M0 processor provides a register bank of 32 general purpose 32-bit registers and a number of special registers. The register bank contains 16 32-bit registers. Most of them are general purpose registers, but some have special issues. Now let us look into a few registers. R14 or the link register. The link register is used for storing the return address of a a subroutine or function call. At the end of the subroutine or function, the return address stored in LR is loaded into the program counter so that the execution of the calling program can be resumed. In the case where an exception occurs, the link register also provides a special code value which is used by the exception return mechanism. Then we have another register which acts as a program counter, that is R15, which is readable and writable. Read returns the current instruction address plus 4, that is because it is due to pipelining, right? So it fetches instructions continuously. Then we have the PSR, either it could be CPSR or SPSR, right? Program register. In this, three types are there: application program status register, interrupt PSR, and execution PSR. If you see the application PSR, then the different flags are negative, 0, C, and V. This is how the register looked. These spaces are reserved spaces, and only this can be used. And we have a few special function registers. One is the interrupt mask special function register. Uh, this special function register is a 1-bit wide interrupt mask register. When set, it blocks all interrupts apart from the non-maskable interrupt and the hard fault exception. Effectively, it raises the current interrupt priority level to 0, which is the highest value for a programmable execution. The PRI mask register can be accessed using special register access instruction MSR or MRS, as well as it can be accessed by instructions called the change processor state instruction. This is commonly used for handling time critical routines. Then we have the control register or spatial register. The stack pointer selection is determined by the processor mode as well as the configuration of the control register. After reset, the main stack pointer is used but can be switched to the processor stack pointer in thread mode. During running of exception handler, uh, only the MSP is used and the control register reads as 0. The control register can only be changed in thread mode or via the exception entrance and return mechanism. I hope you might have got a small idea about the registers of ARM Cortex-M0. Thank you.